So hello everyone, welcome to my YouTube channel. So today we are going to discuss one of the most exciting topics in number theory. So we will now study several useful and charming applications that human creativity can turn virtually every aspect of mathematical knowledge into practical use. So one of the most exciting applications of number theory is cryptology, the study of secrecy systems which can be traced back to the early Egyptians.
So, let's begin. By the way, I'm Christian J. Manito, and I will be discussing a certain topic under number theory, as I have mentioned a while ago. So, what is cryptology? So, we will be answering this question after this presentation or after this slide. There is a famous quote: mathematicians are like Frenchmen. Whatever you say to them, they translate into their own language, and forthwith it is something entirely different. So, cryptography and cryptanalysis. So, when say cryptology, it consists of cryptography and cryptanalysis. The word cryptography is derived from the Greek words kryptos, meaning hidden, and graphein, meaning to write. Cryptography is the art and science of concealing the meaning of confidential communications from all except the intended recipients. Cryptanalysis deals with breaking secret messages. So take note of the word cryptography and cryptanalysis. So it is very important to understand the following terminologies as we go along with our discussion. So plain text is the original message that is to be transmitted in secret form. When I say ciphertext, it is the secret version of that plain text. A cipher, it is a method of translating plain text to ciphertext. The reverse process by the intended recipient who knows the key is deciphering or decrypting, and it is accomplished by a decryptor. The method used by an intended receiver to recover the original message is cryptanalysis. Cryptosystem. Cryptosystem, it is a system for encrypting a plain text to a ciphertext using a key. Kindly look at the given illustration. So from the sender, that is a plain text, then we have here the encrypt, then ciphertext, of course, the secret version of that plain text, then afterwards deciphering or unlocking that ciphertext to back or to get its original version then to the recipient. So different keys are used to encrypt and decrypt message. So we have affine ciphers. We will restrict our discussion to plain text messages written in capital letters of the English alphabet and ignore blank spaces and punctuation marks. In all crypto systems, we first translate each letter to a number. A convenient way of doing this is by numbering the letters A through Z by their ordinal numbers 00 through 25 respectively. Each number is then replaced by a letter. The recipient of the ciphertext substitutes the ordinal number for each letter and uses the key to decipher the numeric message by substituting letters for the various numbers. So, kindly look at the given table. So we have letters from A to Z and we have the following ordinal numbers 00 to 25. for each of the following letters. Substitution ciphers. In a substitution cipher, we substitute a letter of the alphabet for each letter of the plain text. It is, in fact, a permutation cipher since each substitution is a permutation of the letters of the alphabet. Since there are 26 factorial permutations of the letters, there is a total of 26 factorial possible substitution ciphers. One of them is a trivial one, where each letter is substituted for itself. Caesar cipher. Around 50 BC, the Roman Emperor Julius Caesar sent encoded messages to his general Marcus T. Cicero during the Gallic Wars using a substitution cipher based on modular arithmetic. A Caesar cipher shifts each letter by 3 places to the right, with the last 3 letters X, Y, Z shifted to A, B, and C respectively in a cyclic fashion. So it goes like this. This is Caesar cipher. In Caesar cipher, let P denote the ordinal number of a plain text letter and C that of the corresponding ciphertext letter. Then the Caesar cipher can be described by the congruence C is equivalent to P plus 3 mod 26. Take note that we already discussed on how we're going to solve for a particular equation with mod or div in the previous lessons, where P and C is greater than or equal to 0 but less than or equal to 25. Ciphertext is often grouped into blocks of 5 letters to prevent short words from being quickly recognized by cryptanalysts. So let's try solving this example or doing deciphering or ciphertext. Encipher the message "Have a nice day" using the Caesar key. So step 1, using the given table, replace each letter by its ordinal number. Then we come up with this one: 07, 00, 21, 04, 00, and so on, up to 24. Since Y, it has an ordinal number which is equivalent to 24. Apply the Caesar transformation. C is equivalent to P plus 3 mod 26. Then the resulting numbers are 10, 03, 24, 07, 03, 16, 11, 05, 07, 06, 03, and 01. So how did we get that one? So we actually use the Caesar transformation. For example, when P is equal to 24, then C is equivalent to 24 plus 3. That is just equal to 01 mod 26, because 24 plus 3 mod 26, the answer is 01. So how about here? How did we get 10? So 07 plus 3, that is 10 mod 26, that is just equal to 10. So the resulting numbers are 10, 03, and so on. The next step is to substitute the letter corresponding to each ordinal number and group them in blocks of 5. Then the resulting ciphertext message is KDYHDQLFHGDB. So therefore, from a plain text, "Have a nice day," and we encipher it, then we come up with this particular ciphertext message. So it is very difficult to understand if you do not know how to decipher or encipher a given message. So to decipher such a ciphertext, the recipient simply reverses the steps. So from the congruence, we have the deciphering formula. P is equivalent to C minus 3 mod 26, which enables us to recover the original plaintext, as the following example demonstrates. So decipher the ciphertext KDYHD QLFHGDB. So step 1, using the table, replace each number with its ordinal number. Then we come up with this 1. Step 2, using the deciphering formula, P is equivalent to C minus 3 mod 26, retrieve the numeric plaintext. So the resulting numeric string is 0700210400 and so on. Translate these numbers back to the alphabetic format. So always refer to the given table. Then this yields to have a nice day. So step 4, regroup the letters to recover the original message. Then you'll come up with have a nice day. So this is a very important applications of number theory, which is cryptology, because it is widely used, most especially in banks, to maintain privacy and such informations. So I hope that you have learned something in our discussion about cryptology, one of the interesting topics in number theory. So thank you for listening, everyone.
So thank you very much, everyone. So that ends our lesson about cryptology. I hope that you have learned something in my discussion or in my presentation. So before I am going to end, let me give you a quote saying that math may not teach us how to add love or subtract hate, but it gives us hope that in every problem there is a solution. Thank you, everyone, and God bless.